So this is what, or this is where we stopped last time. Covariance of x comma y, two random variables, and I mentioned covariance is related to correlation. And I believe I wrote the expression for correlation, perhaps. I did. So covariance of x comma y is, sorry, correlation of x comma y is simply covariance divided by square root of variance of x times square root of variance of y. That is nothing but the letter R that you might have seen in linear regression. Simply put, the linear correlation coefficient. But by all means, that's correlation coefficient that we have is nothing but a correlation function when it comes to time series, and you will see why when I write this expression involving time. So the reason why we go for correlation is because covariance doesn't actually give us the strength of variability between two random variables. In other words, if I have a large covariance, it doesn't matter that x, or it doesn't imply that x and y are strongly correlated. So in short, a large covariance does not imply large correlation or dependence or relationship between x and y. Hence, the normalization over here, the reason why we divide it by standard deviation is to normalize. Okay, how does this translate to an autocorrelation function? If x above is equal to x sub t and y equals x sub t plus h above, then we would write it as covariance of xt comma xt plus h. I believe your book might use the letter L for the lag parameter that I am denoting as H. So maybe LH, it's the same thing, but I'll put a note here. H is the lag parameter. Or L. I'm going to use H because it is conventional. So the covariance now becomes a function, precisely put, it is a function of the lag parameter H. So as we vary H, gamma H, which is the covariance between xt and xt plus H, will change. So using the same logic, rho H, which is the autocorrelation function this time, ACF, simply covariance of xt, comma, xt plus H divided by, going back up here, all you're doing is replace x by xt, y by xt plus H. Even though we use t plus H, one could also do t minus H, but I don't want you to get confused in the two different notations, because later when we do t plus H, we mean to say a forward forecasting or prediction. That's not what we are referring to. We are just saying, well, if I took one step, what should we expect to happen? So some textbooks, if you read, or if you searched in Google, whatever, t plus H might be represented as t minus H. So, side note, gamma of H is the same as gamma as negative H, in the sense whether you write it as covariance xt, comma, xt plus H, or you write it as covariance xt, comma, xt minus H, they mean the same thing. They are equivalent. Long time ago, when I first started, I mentioned that time series is used in different fields, and one of them is control systems. All we are trying to do is come up with the underlying transfer function of the system. So input, output, H of t is simply the transfer function. I guess they called it transfer function because transfers input to output. That's just a guess. Same picture, we're just going to sort of represent it in a different manner. So, we are going to start with an ARP model. Now, any thoughts as to what P refers to? So P is simply the, oops, that pen. The order, again, if you forget, we are going to deal with linear filters, so eventually this would become a polynomial. So in case you forget what P is, you could always think of a polynomial, you know, order of a polynomial, degree of a polynomial, etc. So P is the order, and your book refers to the time series in terms of the letter Z. I'm going to use X because it is conventional, or rather I should say more conventional, would equal to mu plus psi 1 xt minus 1 psi 2 xt minus 2 psi 3 xt minus 3 plus ... all the way up to psi p xt minus p. Something else goes after that. Can someone tell me what that is? Certainly, the next term would be error. Your book calls it A sub t. I'm okay with it, but the formal notation would be epsilon. I'll put book's notation on the side. Here is a question. What is the subscript for epsilon? Is it t? Is it t minus 1? Is it t minus p? Or is it something else? That is correct. So the subscript is t. Reason being, all we are saying is the current value of the series has some random component epsilon t added at that time. Let's see if you did your reading. So epsilon t, there is an assumption about it. Do we remember? One, we want it to be independent. Another.
Isn't it normally distributed?
Very good. So not necessarily normal, but we can simply call it identically distributed with some fixed probability distribution. The common one epsilon t is normal with some mean, some variance, sigma squared. So I'll put TT there. I believe your book calls it sigma squared A. I'm going to call it sigma squared epsilon because, again, convention. If by some chance I go back and forth, do let me know, but I don't think I will. Okay, So what we have is a series or series expressed as an ARP model. First day of classes, maybe second lecture, I gave mu a name. Undergraduate statistics, we know what mu is. One would hope so. Do we? Mean, very good. So mu is just the mean, specifically the parameter, the theoretical mean that we are going to estimate. In finance, business, econometrics, they call it level. There is nothing wrong with having or retaining mu in the equation, but in terms of estimation, mu doesn't have to be there because it's a constant. I can deal with it later, in the sense when I fit the model, I can get rid of the mean, and then when I come to forecasting, I can simply add the mean back. So what we often do is subtract the mean and write it this way. Xt minus mu. I've not changed the notation yet, so don't freak out because algebraically it doesn't make any sense. Before I change the notation in this expression, if I subtracted the mean at time step t, should it also apply to time step t minus 1, t minus 2, etc.? Yes or no? The question is, if I'm going to express a model where at time step t, I'm subtracting the mean, then naturally should that be happening for all the past times, xt minus 1, xt minus 2, etc.? Yes, of course. So book uses z sub t with the tilde. I'm doing the same thing. From a mathematical algebraic perspective, one might be tempted to write, rewrite each of those x tildes and put it as xt minus mu. I guess I'll just demonstrate it this way. One may do this. Oh, we have xt minus mu. So let me go ahead and do xt minus 1 mu. Xt minus 1 minus mu, xt minus 2 minus mu, ... Rewrite the expression. And do a bit more algebra, if you love algebra, but this is not necessary. It's a waste of time. Why do something when you don't have to do it? Reason being, we subtract the mean when we get data, fit the centered model, which is right here, centered model, And when we forecast, we simply add the mean back and be done with it. So just like in calculus, you add that constant of integration at the very last step. We're going to do the same thing. We're going to do fitting, just like integrating. When we get to the answer, we add the mean back. By answer, I mean forecasting answer. We are slowly transitioning to the transfer function aspects of things. These are very important. At the end of the day, the functions that we are going to write are going to determine the model in its entirety. So pay close attention. I know I have a centered series expressed like so, about there. In terms of the backwards operator, did I use phi or psi? Sorry, I apologize. It's practice or habit, I should say, psi. Don't let the notation of the size give you angst. It's just the notation. The book will use psi, will use phi, will use theta. We are going to do the same thing. Just make sure as to where things go from psi to phi, etc. I'm going to rewrite that expression in terms of B. So uppercase B. What is uppercase B?
The backwards operator?
Very good. It's a backwards operator. Well, how would I rewrite the first term, the backwards operator, in terms of the backwards operator? I'll put psi 1. If you completed the reading assignment, you should know.
Is it BXT?
Very good. BXT tilde. Next. The next term.
Would it be plus psi 2 b squared xt?
Very good. And dot, 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 all the way b raised p x tilde t plus epsilon t. It is possible, you know, for us to write the equation without that epsilon t. Nothing wrong with it, but this is time series, it's stochastic, there has to be error. So retain that epsilon t part at all times.
Professor, do you need psi at the end for the last term?
Oh, thank you. Psi p. Okay. Now that we have the expression in terms of b's, I have xd's in common. Pull that out. So psi 1b plus psi 2b squared dot 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 psi p b raised p xt tilde. Good. Move that entire term to the left-hand side with the error on the right hand side. So I can write it as psi tilde, sorry, x tilde, xt tilde, minus the huge expression that I have, psi 1b, psi 2b squared, plus dot dot dot, psi p, b raised b, xt tilde, equals epsilon t. Well, one more step and we'll be getting somewhere. So I have xt tilde in common between the two terms on the left-hand side. So we take that out. We will have 1 minus psi 1b, psi 2b squared, plus dot dot dot, psi p, b raised p, equals epsilon t. Good. Now, I want you to look at that expression and tell me what that is, what that reminds you of from algebra and bad algebra, speaking of which, they should be negative. The highlighted expression, does it remind you of something from algebra? Give you a hint. I use that word. Very good, Aaron. Polynomial. It is simply a polynomial of order p or degree. I go back and forth between order and degree because of time series. I do it when I teach calculus algebra also. So that is simply a polynomial. It is only natural to ask the question, well, we started by calling the model as a linear filter, ARP model linear filter, and here we have a polynomial, certainly from an algebraic perspective, that could be linear, it could be cubic, quartic, quintic, and so on. So how is this linear? Well, the term linear filter comes from this step right here. Similar to linear regression. We call linear because it is linear in terms of the predictors. So same logic. So don't let this confuse you, because this is definitely not always going to be linear. It could be linear, it could be quadratic, etc. But we call it linear because of our model definition. Okay, next step, I am going to rewrite the highlighted part. This is my uppercase psi. I'm just going to write psi bigger. Equals epsilon t. Divides by uppercase psi. Write it that way. One more step, algebra. psi inverse of, sorry, psi raised -1 of b. My brain is going ahead of me. That's surprising, it's only 9 something. No, you know, in algebra, professors might put this in red or whatever. 1 over f of x is not equal to f inverse of x. So there, in terms of notation, that is the inverse function. Here, in terms of notation, it's not the inverse function, it's just the reciprocal of psi b, i.e. Psi b raised -1. So don't let that part confuse you. We are not referring to the inverse function for psi b. Good. That's why I always say there is a difference between thinking like a mathematician and thinking like a statistician. Never an actuary. Oops, what just happened? You see how things go wrong the moment I say it? Okay. Any questions before we move on? So are we able to connect the dots at this step and go back to this picture? Is it making sense? Yes or no? We'll start there. The expression that we derived and that picture. Take note of the picture. Back to the expression. So is this mission accomplished or is this mission impossible? So when we first started, we had x of t goes into this black box. H of t results in y of t, or y sub t. Then 45 minutes ago, now do we agree with that statement? Or picture? So, oh, I wrote it backwards. You shouldn't agree with me. Epsilon t and that. Epsilon t goes as input inside that black box, which now represented by psi raised -1 of b, output xt tilde. So what did we find, or how did we rewrite the model? We rewrote it in terms of psi raised -1 of b, which is nothing but the blank function. Are we able to fill in that blank?
Yeah,
what
that's
is
the reciprocal function.
true. But going back to the beginning of class, Joe,
The
very
transfer
good.
function?
Transfer function. So all we are doing is we are estimating a transfer function from a control system's perspective. What they call as transfer function in signal processing, control systems, etc., time series, we simply call it as a model. I say tomato, you say tomato, we're all talking about the same thing. Are we clear? Not seeing any questions. If you do type or unmute and ask. Do a quick example before I dig deeper. Suppose the fitted model for some series that we observed xc tilde minus 0.82 b, oh, let me write it this way, xc tilde minus 1 or equals epsilon t. And is it possible for us to find epsilon t and psi t, or estimate, you know, something about epsilon t, the entire psi function, the psi raised -1 function, etc. I'm picking the simplest case. So first step would be to rewrite the series that I have, xt tilde minus 0.82b, xt minus 1, oops, xt tilde, equals epsilon t, xt tilde is the common factor, so I can write it this way. And if I asked you, well, what is psi of b? What would your answer be? So psi of b is simply 1 minus 0.82b. Divide by psi of b on both sides. One over 1 minus 0.82b epsilon t. What is psi raised -1 of b? I'm trying to avoid saying psi inverse because there are math majors here. They will take offense. That's what I got, and that simply psi raised -1 of b. Any questions so far? So what I'm going to do is rewrite psi raised -1 of b as a series. Side note, so geometric series. The infinite sum of a geometric series is simply on the right-hand side, 1 over 1 minus a. The terms that you're summing is simply a raised k. So instead of a, in our case, we have 0.82b. That part right there is simply a in my side note. So I can write the box part as sum I equals, I'll just use k. K equals 0 to infinity, and 0.82b raised k followed by epsilon t, or a sub t. We go with the book's notation. Do we agree with that expression? Sideways m is just uppercase sigma, which means sum. So what I will do is I am going to plug in k equals 0 followed by 1, 2, etc. So when I plug in k equals 0, 0.82b raised 0 plus 0.82b raised 1, 0.82b raised 2 plus ... It's going to keep on going. Epsilon t. First term's easy, it's just 1. 0.82b, second term is easy. The next term we've got is 820. 0.984. Did I do that right? No, something seems off. No, 0.65 something. 66, I believe, but do check. I'm not using a calculator, I'm doing mental math. So 0.65 b squared plus ... and it keeps on going, plus epsilon t. And the expression that we have, oh, sorry, not plus, times epsilon t. The expression that I have inside the square brackets is also a polynomial. So what I'm going to do is distribute epsilon t into that polynomial, write it as epsilon t plus 0.82b epsilon t 0.65 b squared epsilon t plus dot, dot, dot. Leave it at that. Second term, I don't want, 6, 7, thank you. And it was 6 something. But definitely not 0.64. Okay, the second term, b epsilon t, I don't want to see uppercase b. So how can I rewrite that second term in the expansion without b? Think, what does a backwards operator do? If you answer that question, you know how.
xt minus 1.
Very good. Epsilon t minus 1, 0.65, epsilon t minus 2 plus dot, dot, dot. Here is a question. Does that remind you of something from day 2 of lecture, I believe? Hint, it is another time series model. Think of the examples that I used in class. xt, depending on xt minus 1, is auto-regressive. In other words, whatever you are today, you're going to decide based on what happened yesterday. You are auto-regressing. The other case, think of the movie series or book series of unfortunate events or fortunate events. So whatever random events that had happened in the past represents you today. That is my hint. That said, what does the expanded version on the right-hand side resemble? So the right-hand side is nothing but a moving average. Any guesses on what the order is? Omar says P. Here's a question. Did I stop at P? Andres, correct. It is an MA infinity process. So what I simply did is I took an ARP process and I rewrote it as an MA infinity process. So important notes before we dismiss. So no matter what series that we are observing, there is a connection between AR and MA. You can write one in terms of another. One is called filtering, the other is called smoothing. I'll get into more detail later. So I took an ARP model, sorry, AR1 model, and where is it? Right here, AR1 model, and wrote it as an MA infinity model. So in this case, AR1 became MA infinity. That's a good place to stop for today.